Exponential and logarithmic functions. What was how to evaluate exponential functions, graphs of exponential functions, and evaluating exponential functions with base e. Now let's start with exponential functions. What is an exponential function? I mean, basically, an exponential function is in this form. So b is a constant here, and x is the variable, and we have some conditions on b. So these are necessary conditions, like b should not be 1. So if it is 1, we have this 1 to x, which is 1 all the time. So it's a constant function. So for this reason, exclude this b equal to 1 case. And the other thing is b should be bigger than 0. Otherwise, there will be some negative number. And this number, for example, it will be hard to calculate, and it will not be a complex number. It will be a complex number, not a real number. So these two conditions on b are important. And we call this the exponential function with base b. Base b is the base here. And the difference between exponential functions and algebraic functions is here. One is using the x is the variable. I mean, both x is the variable, but x is the base in the algebraic function, and in the exponential function, x is the power here. So the power is the variable here, the exponent is the variable, and the variable is the base in algebraic functions. When saying algebraic functions, I mean like the polynomials and this type of the power of x type functions. And when evaluating exponential functions, we might need to use calculators, of course. Like okay, when calculating this is it's easy, but how about calculating this one, 0.153, for example, or what about 2 to square root 2? How can we calculate them? So we need to use calculators for it. We know how to do this, and we know the meaning of this, and how to get here is we can, okay, this computation of these and these, it requires some numerical methods, and we will not get into that. It requires some more, more advanced level mathematics and numerical methods. So we will just say the numerical values of these and the decimal approximations of these, and they can be found by a calculator. There is a mathematical base for it, but well, I will not get into that. Okay, now the exponential properties, you know them from the last semester. We have already seen them. These are the basic properties of exponential numbers. And let's see how to evaluate. It says evaluate the exponential function for x equal to 2, x equal to minus 1, x equal to square root 2, and x equal to pi. So it's basically asking what is f of 2 here, what is f of minus 1, what is f of square root 2, and f of pi. So nothing is different than the evaluating a function. Just substitute the value here 2 for x in the formula. So it's like that. Now f of x, like 4 squared minus 1, you put here minus 1, your x, the square root 2, and you put the square root 2 to the power, and this pi and pi. And now for these, you can use the properties of exponential functions here. 4 squared, 4 to the negative first, it's 1 over 4. But for these, for the irrational numbers and for more complicated numbers, we generally use the calculator. We use the calculator if we need a numerical approximation. And let me tell you, this is not equal sign. This is approximately. It says approximately. This means this is approximately, Arabic it's تقريبا, approximately, so approximate value. So these are like the numbers like pi, so they never end, but we have to cut it cut it somewhere. So we give you the approximate values, and here is the evaluation of g of 2 and g of minus 1, g squared through, and then g of 2, g of pi. So we again use the properties of exponentials if we are evaluating the integers, but for the others, I mean, we need still calculate it, and we will find the approximate values of these numbers. Now again, it's the same thing. You just put, x is 2, then you put here 2, you substitute 2 minus 1, square root 2, like pi, you put it here. And by using the calculator again, we find these. Now graphs of exponential functions. Okay, let's try to make the graph of some this function here. This is an exponential function. 2 to the x, and we can make a table and see what's happening for different values of x. Now x equal to, let's say, minus 3, minus 2, and minus 1, 0, 1, 2, 3. Let's look at them. This is 2 to negative 3, which makes 1 over 8, and this will make 2 to negative second power, so which will be 1 over 4. And 2 to negative 1, so it will be 1/2. 2 to 0 power is 1, 2 to the first power is 2, and here this is 4, this is 8, as you see. And now when we put these values on the graph, negative 3, okay, let's say this is negative 3, and it will correspond to 1 over 8. 1 over 8, let's say. And then for minus 2, we will have a little more than this. Okay, it will be hard to do it with this scale. It's 1 over 4. And then minus 1, 1 over 2. So it will come to here, something like that, 1 over 2. And okay, for 0, we will come to 1. The units in the x-axis and the units on the y-axis are not same. Okay, by the way, I mean, according to my look, this is 1 here. 1 unit is here on the x-axis, and there's a 1 here in the y-axis. So I'm not using the same scale, okay, for x and y. But okay, 1, 2. 1, 2 is here. And 2, it's 4 somewhere here. So 3, it's 8 somewhere here maybe. Now when we look at here, there will be this graph here. Okay, this is the graph of 2 to the x. Now you will see it. I mean, we have the graph of it, and I mean, clearly we have it here. The same thing is done here, and when the points are placed, I mean, we see this type of graph. Now let's look at the properties of this graph. First, the y-intercept is at 0, 1 for sure. There's no x-intercept here, so be careful about this part. The graph here, the graph doesn't touch the x-axis. So this here in this picture, I mean, it looks like it's touching no, and theoretically, I mean, this is never happening. Like, it will get closer and closer to here. It will get closer and closer, but it never get to 0. So it will never touch the x-axis. Okay, and one other thing is like how to get the x-intercept. You set y equal to 0. You remember that? So 0 is equal to 2 x, and then you find it, and there's no such x giving, I mean, 2, the power of 2, any power of 2 is bigger than 0. I mean, yes, so for this reason, so there is no solution for this equation and no x-intercept. So mathematically, we were finding it this way, and graphically, it means the graph does not touch the x-axis, and it doesn't touch, but we have this phenomena here. It doesn't touch, but it gets closer and closer as x gets to negative infinity. So the difference between these two, these two curves, the curve and this x-axis is getting very close, smaller and smaller, but never same. They do not overlap or coincide. So this line here is this boundary here, the lower bound is called the horizontal asymptote. So horizontal asymptote for the curve. So here in our case, y equal to 0 line, this line here is y equal to 0 line, also we call it x-axis. So this is making the horizontal asymptote of the graph, the function. And the range of f of x is 0 to infinity. So how can you know from the graph? So you just basically put these values here. You take the projection of the curve or of the graph onto the y-axis, and the collection of these points, like starting from here, but it's not included, the 0 not included, but these points, all these points, there are the projections of the points on the graph onto the y-axis. So it makes the range of the function. Now the domain is, as you know, now we are checking the projection onto the x-axis. So as you see here, the graph does not stop anywhere, so it goes endless. So it will cover all the x-axis. So we say the domain is minus infinity to infinity, and this f is increasing when you go from left to right. This is clear. So these are the characteristics of such function, and this will form the characteristics of the similar functions. Now let's look at this function here, 1 over 2 to the x. And now let's do the table for this function. Like this is 0. Okay, let's start from some negative numbers here. So let's start as usual. This is -3 and the 1 over 2 to negative third power. You can write this one as 2 to negative first power, then -3. So then you will have this 2 to plus 3. So it will be 8. In the same way, you will see this is 4. In the same way, you will see this is, okay, 1 over 2 to negative first power, it will be 2. And then 0, it will be 1. And then 1 over 2, no, sorry. This is 1, it will be 1 over 2. And then 2, it will be 1 over 4. And then 3, it will be 1 over 8. So we have a different behavior here. So it's like that. When it is -3, we have a big value here, like 8. And when it is -2, we have 4, just half of 8. And then -1, it makes it makes 2, half of 4. And then at 0, this is 1. This is 2, this is 1. And for the positive values, it gets less than 1. So for 1, again, it will be half. and for 2 it will be less, and for 3 it will be less. So it will get smaller and smaller. As you see, the behavior of this function, this exponential function, is different than the other one, the previous one. When x gets to a big number, big positive numbers, the graph tends to approach the x-axis, and for the negative values, it's getting higher and higher. Okay, let's see if we have something. Okay, now again, we can check the properties or the characteristics of such graph. It has y-intercept again at the same place here, 0, 1, and there's no x-intercept. Here it doesn't stop, it goes this way, but you know there's a difference between the x-axis and the graph. So the graph comes very closer to the x-axis, but it never touches. So there's no x-axis, and the x-axis is the horizontal asymptote because of this behavior. So as x gets bigger, the graph gets closer to the x-axis, but it never touches. The range of f of x is, okay, you take the projection, it gives you the same thing, 0 to infinity, and the domain, take the projection of the graph onto the x-axis, you will get this set, and f is decreasing, as you see, from left to right. When you move on the graph, you go down. Okay, okay, let's put these two graphs now with some generalization, like b is bigger than 1, so we have this type of graph, and if b is less than 1, we have this type of graph. So we will list the characteristics of the exponential function now. The basic exponential functions will behave like this or like this, so depending on the base. So now let's see, the domain of both exponential functions have the same thing. Like, look at here. The range, look at here. Same. In both, like, the graph is passing through 0, 1, as you see. The same. This is 0, 1. Is the y-intercept is 1. This is the common property. And both graphs, they do not touch the x-axis, so no x-intercept. And the horizontal asymptote, you know, we have this phenomena here and here. As you see, when x gets larger and larger, the graph is becoming, very close to the x-axis. And here the same thing happens. So these are the x-axis is the horizontal asymptote of both graphs. And if b is bigger than 1, it's increasing for sure, and this is decreasing for sure. And one other interesting thing, important thing here is, in both functions, when you make a horizontal line, it passes through only one point here, right? It cuts or it intersects the graph at only one point. Any horizontal line is passing through only one point here on the graph. Okay, or it doesn't intersect. Anyway, so this property, we call it the being one-to-one. So the functions here, b to x with b bigger than 1, or b to x with b less than 1, they are both one-to-one function. So what does this imply? If a function is one-to-one, what can we say about this function, or what is special about being one-to-one? If f is one-to-one, it has an inverse. It has an inverse function. Okay, we will come to that in the inverse function. What is the inverse function of an exponential function? Okay, you can guess it. It's the logarithmic function. So the inverse function of the exponential functions is logarithmic functions. In real life, sometimes we use the word the exponential, and most of the time it's about exponential growth or exponential decay, especially in biology or science. The exponential growth is a common term, and exponential decay. Here, the exponential growth means like the assume this is a time, okay, and this is the population, let's say, population of people or number of corona cases, for example. So if it is increasing very rapidly like this one, if it gives you this behavior, by the time it goes like very high, so this type of growth is called the exponential growth. Like as you see, for example, let's say, remember that the days, day one, this is corona cases, let's say. This is day one, you have only one people. Day two, you have like two, and day three, and you have day one, let's say two. Day two, it's 4. Day three, it's 8, and day 4, it's 16 and 5. It makes an exponential growth here. So, the behavior of the corona cases is like that. It was like that in the first 3 or 4 months. It was like that. Then it changes this way. I mean, look at the statistics. You will see the corona cases versus time in the world. So you will see it starts very, relatively with small values, then it goes very high, then it becomes steady, and we are expecting to go down, but this behavior here is, we call it exponential growth. Okay, this behavior here, we call it exponential growth, not the other part. Okay, and exponential decay is if something is going, by the time it's rapidly going very small, falling down, so we call it exponential decay. And this exponential decay, maybe in biology or chemistry we have such a phenomenon, exponential decay, but its graph is this way. Like if someone told you that there's an exponential growth in something, economy, and the amount of something, so you will think of it's going very, very high, like 2 to the x. But if it is exponential decay, it means like it's going decay very fast, falling down very fast. The procedure for graphing the function b to x, it's basically this here is telling you, it's basically telling you just to put 0, put 1, and -1, and find these values here, and make the graph. If you have 3, or one of them is here, one of them is here, one of them is, okay, 3 is enough. Like if the function is this type, like the finding the values 0, 1, -1 is enough to make the rough graph of the function. Then of course you connect them, make a smooth curve, and remember this x-axis is the horizontal asymptote. The graph will not touch the x-axis, but it will get very close to it. Let's look at 5 to x and its domain and range, and x-intercept, y-intercept if they exist, and determine whether the graph represents an increasing, decreasing function, and the equation of the horizontal asymptote. You can get this graph by doing this, x, 5 to x, and put the values if you like here. This one, I'm taking some more here. Okay, I'm taking this -2 also, and then here 0, it will be 0 is 1, and then 1, 5, and 2, 5 squared. Okay, if you put them, here the points, you see 1, 5, and 2, 25 somewhere here maybe, and then 1 or 5. When you put the numbers 0, 1, you will get this graph. Now what can you say about the domain and the range? The domain is from minus infinity to infinity, and the range is 0 to infinity as usual. And the x-intercept, there's no x-intercept, like there's no touching the x-axis here. Just the picture is showing this way, but when you zoom in here, when you magnify this part, you will see they're not touching each other. This y-intercept is here, as you know, this is at 0, 1, so the function is increasing for sure from left to right. The equation of the horizontal asymptote, so look at the horizontal asymptote, which means this graph is approaching to which line? This line is the x-axis. What's the equation of this line? Okay, let me remind you, if a horizontal line, for example, passing through -5, we say it's y equal to -5. So it's passing through a 0 level, and it's, what is this then? Y equal to 0 line. Or we call it the x-axis. Okay, let's graph sketch the graph of this function here, and we will use the graph of the basic exponential function 2 to x. Now, as you see, this function can be obtained by some algebraic transformations from f of x. We have seen the transformations, like the functions, the transformations of functions. The one thing you can say is like this big f of x is indeed like the f of the little f of x minus 1 plus 2. Now, the question is, how can you get the graph of such function here? So you transform f of x to this one, so how can you make how the graph is affected? So this is 2 to x, and this will be 2 to x minus 1 plus 2. So 2 to x is, we know it has to be something like this. So, okay, generally I do it this way. Maybe you learned it in some other ways, but this is how I do it. 2 to x becomes 2 to x minus 1, and then 2 to x minus 1 plus 2. So here x is replaced by x minus 1. And now this gives you, okay, this f of x becomes f of x minus 1. So this type of change gives you what? Shift 1 unit right. And this type of behavior, this function and this function, now it's added plus 2. So this, okay, this, like you add plus 2 to the function, this means shift 2 units up. So it will be shifted 1 unit, then 2 units up. So then you will have what? This will come to, okay, this will come to here, and then will go 2 units up. So you will have such thing. And in this, be careful about the asymptote. The asymptote will be lifted also 2 units. So the graph should look like this then, okay? So this is how you get this one. Okay, let me make it clear. 1 unit right, 1 unit right, and 2 units up. So this point, let's say, if it's 1 unit, and this is 1, it makes 2. So then this point comes to here, and this one, this asymptote, yeah, we take it to this side, the asymptote does not change, but when we shift it 2 units up, the asymptote will be shifted 2 units up. So, okay, let's see how it is done. So here, the new graph will look like this. It was something like this. It was passing through 0, 1. It was going like this, so it will be shifted 1 unit and then go up. So 0, 1 comes to 1, 3. 0, 1 comes to 1, 3 by the shifting, and you can find the other values, but simply make the table. I mean, you can use the transformations, or you can use directly make the table of this and see the graph if you like. But here it says use the graph of this, so we have to use the transformations here. And so this will be the graph of this. This will be 1 unit shift and 2 units up, and then here, as you see, this asymptote will be lifted to 2 units up. So this asymptote will be y equal to 2 line. And the domain and the range, okay, the range will be lifted up also. It starts from 0 here, but new one will be 2 to infinity here. So it will start here like you have this, and it will start from 2, will go to infinity, this. And but the domain will not change the projection onto the x-axis, and y equal to 2 line will be the asymptote. Again, as I said, like you can make the table and see it, of course, if you don't want to use the transformation. So here we can do the transformation in the same way: 3 to the x, 3 to the x minus 2, and then 3 to the x minus 2 plus 1. So this makes shift 2 units right, and here shift 1 unit up. Now it makes, okay, if it is 3 to the x, so it has to be like that, and 2 units right, so it will go 2 units and then 1 unit up. And now this point will come to here, and the asymptote will come to here, same level as yeah, somewhere here. We'll come to this. Okay, we'll come to this. So about the horizontal asymptote, only this part will contribute. Only this part will change determines the new asymptote. It was 0, and it was y equal to 0, but this time y equal to 1. So here, this is what is this? This is 3 to x. Which one is 3 to x? It is this one, 3 to x, and then we shifted 2 units. So it became this. It's 3 to x minus 2, and we shift this one unit up. So this here, the red one, is 3 to x minus 2 plus 1. Now, as you see, the asymptote has been lifted 1 unit up because of this here, 1 unit up. So we can think, okay, the domain does not change, the range changed because we lifted the function up, so it doesn't start with 0, it starts with 1 level. The x-intercept, no x-intercept, y-intercept is what? Okay, the y-intercept here is what? Now how can, so you can see the y-intercept is somewhere here, but how can you see it? You can just see how to find it, like make x equal to 0 and see this one. So if you do the calculation, then the y-intercept will be 0, 0, 10 over 9. And the equation of the horizontal asymptote, since it's lifted 1 unit up, so it will move to y equal to 1 line. So this is, as you know, this is y equal to 0 line, and now it moves up to y equal to 1 line. So this is the new asymptote for the red line. So red line is this one. Now evaluating exponential functions with base e. Okay, I think this is the first time you see For most of you, this is the first time you see the number e. The number e is something like pi, but it has a very different value, 2.717182 and more. So we just cut it here. So it's, pi is also, it is endless, but we cut it here or we cut it here, and we can cut it here or we can cut it somewhere here. It depends on your, it depends on what you want to do. If you're doing a precise calculation, you might need more decimals. Okay, this e is a very, very important number in mathematics. It has nice, very, very nice properties. The mathematicians found it, and as far as I know, I think they attribute it to Euler. I think Euler found it, and yeah, as far as I know, Euler. Anyway, this is a very important number in mathematics and also science. And this, so instead of writing this big number here or writing this everything, pi has this 3.14 or something, and we don't write 3.14, right? We just write pi. So when we say pi, you understand this is 3.14, 15 something. So from now on, when we write e, you have to understand this is 2.717182 and so on. Now, f of x equal to e to x is called the natural exponential function. So it has a name, natural exponential function. Now, about this function, it has very nice properties in calculus. You will see its derivative is equal to itself. And we have this Euler's formula, e to I theta is equal to cosine theta plus I theta, I sine theta. Maybe you have seen this one, but no one told you this one, I guess. So anyway, so these are very important properties of e. So for this reason, it's used in mathematics. I mean, we teach you here. And evaluating this e to x. Okay, let's look at e to 0, which is 1. E to 1, this is just e, and which is about 2.717182. And when you come to e to 3, you have to use calculator. And for this one, you have to use a calculator as well. Okay, let's see how it is. Okay, as you see here, this is about 2.7171, so approximately 72. The e cubed with the calculator, you can approximate it, so it's 20.09. And e to negative square 3 is approximately 0.18. Okay, we need calculator. Okay, needs calculator. We need calculator. And the graph of e to x, it's not, typically, it has the same properties as any other exponential function. This e to x is, since e is bigger than 1, so it will have such behavior. And when it comes to e to minus x, which is 1 over e to x, right? This is e to minus 1x, 1 over e is less than 1. So it has this type of behavior, as you see. Now, if you ask, okay, what's the difference between like 2 to x and e to x and 4 to x? 2 is here, let's say, and e to x is a little that, and this 4. It's like that, it gets steeper. So this is 2, this is e, that's a 4 to x. So if you increase the numbers here, the bases, so it will get a steeper function graph. But anyway, e to x and negative e to x is this, and also you can look at this. You can see the behavior of this graphs in terms of the functions transformations. You have f of x and you have f y equal to f inverse. I mean f of minus x. So you see there they are a reflection of each other with respect to the y-axis. You know, when you change x with minus x, you take the the reflection of the graph with respect to y. I mean, this is another thing to note here. If you remember the the transformation, like you flip this one according to y-axis, and you get this graph. Or if you do it this way, I mean, you get the other graph. Okay, now we have another section. We will learn how to convert exponential expression to logarithmic expression and vice versa, and use common and natural logarithms, logarithmic functions, domain of a logarithmic function and base, using basic logarithmic properties. Now, now we introduce the logarithmic function. Now, b, the base function, I mean, the base should not be 1. Okay, b is not 1 for sure. This is important. And b is always positive. And here x is always positive. Now, we define the function f of x, log base b of x, we call it. We read it as log base of b of x. What does this mean? The log base b of x is equal to y if the x is equal to b to y. So what is the meaning of log b of x? This is answering this question. Which power of b is equal to x? Now, ask this question. Which power of, okay, let's make it 8. Which power of 2 is equal to 8? So which power of 2 is equal to 8? It's 3, right? So this means if you write this equality, it means 2 cubed is equal to 8. So this is what it is telling here. Let's do some more exercise here. Which power of 2 is 1 over 2? So you say this should be equal to minus 1, right? Because, and what does this mean in terms of exponentials? This is 2 to negative first is equal to 1 over 2. And let's do some more exercise. What is, okay, let me ask you this one then. What is this? Square root 5. So what is this? So this is asking which power of square root 5 is 5. So the question is here, which power of square root 5 is 5? It's 2, right? So this is 2. So you know it's 2, it's 5, so you write it this way. Now, do you understand now what does this mean? Like this x equal to b to y. If this happens, then we can say it's y equal to log b of x. Or if this is given, then you can write x equal to b of y. And I can change the question to this one here. So what if I write this? What happens? Which power of 5 is squared 5? Do you remember that? This should be what? So it's definitely 1 over 2. If you remember, it's 1 over 2. So you write here 1 over 2. Okay, there are some, of course, there are uh, some powers that we cannot find. So, for example, what is this? Which power of 2 is 3? Okay, I don't know. I asked the calculator, but the calculator will give you some numerical values, 1 point something maybe. But in any case, if someone asks you this, like which power of 2 is equal to 3, we call this power log base b of 3. We don't know the number exactly, but we say it's the log base 2 of 3. So it's the power of 2. I mean, the 2 to that power will be equal to 3. Okay, some important points. As I said, they're equivalent to each other. So, saying this and saying this, they're same. I said, like saying this 8 is equal to 2 to 3 is the same as saying the log base 2 of 8 is equal to 3. So they're same. And we call this part the exponential form. And we call this form this logarithmic form. So in our coming examples, you will see the transformation, like the conversion process. Like we will ask you to convert this one to logarithmic form, or ask this one and convert it to exponential form. Now, how can we write them in exponential form? So it means like 2 cubed is 8. What does this mean? 10 to the first power is 10. E to 0 is 1. Like this is base. And the log always gives the powers. So 3 to negative second power is 109. So if I write this one, okay, it's a challenge, okay. Now, from here, it's easy to find out, okay, so how can you say this one? What is this? What is this? This is x, the base. This is power. A is equal to y, okay? So don't forget this. Let's do the try and check. 4 base squared 16. 16 to 1/2, 4. 2 to negative fourth is 1/16. 1/3 to negative second, 9. So you can check them. Now we will do the reverse now. We will take this one and try to write it in logarithmic form. The base, okay, look at the base. The base is 10, so you have to write here 10. And the power should be here 3. And this guy should be here. So 10 cubed is 1,000. And what can you say about this? The log base 2 of 1/2 is -1. Log base 9 of 27 is 3/2. And here you can write this one as like 7 is equal to 49 to 1/2. So you can write here log base 49 of 7 is equal to 1/2. Now let's do the logarithm here. So we say log base 3 of 81 is 4. Log base So what is this? 121 1/2 power. So it will be the log base 121 of 11 is 1/2, and then log base 8 of 1/64 is the power. It's -2. Okay, please stop the video and try to do it by yourself, because it's not easy to remember if this is the first time you see it. You do the worksheet problems and do the additional problems so that you get used to it. If it is your first time, you have to look at here again and again. And after some practice, I think you will get used to it. Now let's try to do this, like do the conversion when doing the inverse of a logarithmic function. Okay, it will be okay. We will see the inverse of logarithmic function now. Now, I will do it my way, like we teach it this way in Math 111. So I will do it this way. So I was doing this y, and then you switch x and y, but I will not switch. Okay, I will not switch. So I tried to solve it for x, and this is the idea. I mean, solve it for x, but how? Can I use this log thing? Yes, I know how to convert this one, but this +4 is separate. Okay, it's a separate thing. Don't put it inside. You cannot. Okay, don't do it. So the only thing you can do here is like send 4 to the other side, and then you have some log expression. Now convert this one to the exponential form. What does this mean? The base is 3. And what power of 3 makes this? This is 3 to the y minus 4 power is equal to x minus 1. Now what is x? So you send this one to the other side, and then you change x with f inverse of x and y with x. So this is the method I use. Now you can use other methods. I mean, as long as your answer is correct, so there's no problem. But okay, what does this mean? I mean, does it contribute or does it bring some condition to us, like y bigger than 1? Indeed, it will not affect, but I want to show you why. I mean, why? X bigger than 1. So you see here, x is still bigger than 1. I mean, we find something here, like we find this one, x bigger than 1. See, so this condition does not change anything here. You know, this condition we generally ask, like if you have plus or minus issue here, you check the condition here. I mean, in the restricted domain issue, but here there's no two values, so we don't have to check this x bigger than 1, because x bigger than 1 is to, this condition is given to guarantee here this is positive. And for the inverse, there is no problem for the x. I mean, for the x can be anything here, but this x and this x and this x, they're not same. Okay, this x applies to here, not here. Okay, because we changed x with y with x here. So here we find the inverse of it. Okay, now let's. Okay, I think I skipped a step here. I mean, the try and check exercise, but it was saying this f of x is equal to log 2 x plus 1 minus 4. And then it says find the inverse of x. So the first thing we write this way, y equal to log base 2 of x plus 1 minus 4. And then send 4 to the other side. Then convert this one to the exponential form. And you know, this is base, this is the power, and now this is equal to x plus 1. And then make x, isolate x. Now 1x is equal to this, and change this x with f inverse of x, y with x. So you end up with the inverse of this function. Common and natural logarithm. Now in in the calculators and the computers, you will see log x. You know, we always teach you logarithm with base. So, but when you look at the calculator, you will see log x and there is no base. So this is a common notation for log base 10 of x. So we call it common logarithm. So here, if you don't see the base here, it means automatically it's 10. And you will see another one, which we call it ln x. So ln x is a natural logarithm. We call it natural because we have the natural exponential base, so which is e. So the number e, you remember this, 2.7171 or 72, it goes like this. If someone give you this ln x, so it means the logarithm of x, logarithm base of e of x. So these are the two common logarithmic functions, and these are the ones you see on a calculator. On a scientific calculator, you see the log of x and ln of x, so it means like base 10 of x and base e of x. Now these are some practices with calculator, and round your answers to 3 decimal places. Okay, I will tell you what does this mean, round your answers to 3 decimal places. So for example, you got an answer like this, 0.5389 or like 7, 5, it goes like this. So we want the first 3, and then rounding happens like if this is bigger than 5 or equal to 5, then you change this one to 9, you increase it by 1, and then you erase this one. So it becomes, it's rounded now. Now if it is like 5382, since this is less than 5, you just erase this one. You do not increase 8 to 9. So this is how you round them. Okay, these are the practices. You can use your calculator and see. Now, what does this mean? Like this means like 10 to, oh, sorry. First, let's use the values. So let's see the calculator values. Yeah, approximately these are the values. You can use calculator. For example, like what does this mean? This is log base 10, so it's 10 to 3.305 is approximately 2017. And you can convert the others to the exponential form if you need. Graphing logarithmic functions. You know, these, as we said, these are the inverses of each other. Inverses of each other. These are the inverses of each other. I can show you that one. Y equal to log b of x. And when you convert this one, it will be b to y is equal to x, then change y with x, and then change x with f inverse of x. So as you see, this function has its inverse as b to x. Now, what's the relation between the graphs of two functions? What is the relation between the graphs of two inverse functions? If you remember it, you do y equal to x, then if this is f of x, then you have f inverse of x, right? Here, the reflection with respect to, they have to be symmetric with respect to y equal to x line. Now, we will use it. Now, I want to show it to you. So, as you see here, logarithm, 2 to x is this graph, and look at y equal to x is this line here. And then the graph, the inverse of 2 to x, which is log base 2 of x, will be just a reflection of the graph of the exponential function with respect to y equal to x line. So you can take And you see, so we have some interesting behavior here because this horizontal asymptote now became a vertical asymptote for this function. So if you look at the properties of this, like now it's there is no there for the exponential function we have these properties, but for the logarithmic function we have x-intercept here. Whereas this one there's y-intercept here, but there's no y-intercept for this one. So there's y-intercept for exponential function, but there's x-intercept for logarithmic function, and no y-intercept here, and here no x-intercept, you know. And the domain is 0 to infinity. I mean, look at here, domain. The range is, you know, look at the projection onto y-axis. And there's vertical asymptote. The vertical asymptote is the y-axis here, you see? The y-axis is the vertical asymptote for the logarithmic function, and the logarithmic function does never touch the y-axis. Now, these two functions, like the logarithmic functions and the exponential functions, should be one of the basic functions, like two of the basic functions that should be in your library, at least in your brain. Okay, these two types of functions, exponential functions and logarithmic functions, should be in your brain. Okay, in the library of your brain or in your mind. Okay, like because in calculus and the other courses, then the teachers will use these functions, as you already know, so you have to know them. Now let's look at the properties of logarithmic function. The properties of the graphs of logarithmic functions. Now here we see if b is less than 1, this is the graph of log base b of x. And if b is bigger than 1, this is the graph of log base b of x. Now, when you look at the graphs, I mean both graphs, the domain is from 0 to infinity. So it means you can put only positive numbers here. This x should be positive here. So the domain says x should be positive, and you can see it from here. If you take the projection onto the x-axis, you will see the domain. It starts from 0 and it goes to infinity. And the range, if you look at the range, the y values, they take the projection onto the y-axis, so you will see it's all real numbers. You can do it with the red line and the blue line, it will give the same thing. And they both pass through 1, 0. So in the they have the only x-intercept at 1. And the vertical asymptote, they have both vertical asymptote, like here the vertical asymptote is y equal to, no, this x equal to 0 line, which is called also y-axis. And increasing if b is bigger than 1, so, and if b is less than 1, it's decreasing. Now let's look at this question here. It says graph the following functions and state their domain and range. Now they look at here, these are like the base 2, log base 2 of x, and here this log 10 base 10 of x, and this is you can write it as log base e of x. So here their graph will look like, you know, okay, look at the base. The base is 2 here, the base is 10 here, and they're all bigger than 1. And then e is something like 2.71, and which is bigger than 1. So we have a graph like the blue graph. So b is bigger than 1. This is the graph of log b of x. Now, look at the domain and the range. So the domain and the range will be, as stated here, it will be from 0 to infinity. This is the domain. And the range will be, again, from minus infinity to infinity. So for all of them, the domain is same and the range is same. Finding the domain of logarithmic functions. Sometimes we might have some shifting or some function inside the logarithm. Here, the important thing to keep in your mind is all the time the term inside the logarithm should be always bigger than 0, because the domain of log function is from 0 to infinity. It means, well, whatever you put here should be between 0 and infinity, so it requires this 2x plus 3 is bigger than 0, and this x squared minus 2x is bigger than 0, and here you have to say the absolute value of x minus 2 bigger than 0. So the solution, okay, the domain of this set, this function will be the solution set of this inequality, and the domain of G will be the solution of this inequality, and you know how to do this. And the domain of H is the solution set of this inequality. Now let's see how they are solved. Now the logarithm requires 2x plus 3 bigger than 0, and then send 3 to the other side and divide by 2. You get this one, and now this becomes, okay, this means we have this interval, so the domain should be this interval, and then we have to solve x squared minus 2x for the second function, and then we find the roots of this one here. This is in standard form, so we find the roots of the polynomial, which is 0 and 2, and then we make the sign chart, and then we check. So we see this is plus, this part, this is minus, and this is plus, and we are interested in the plus part, and the roots are not included because there is no equality. So it will be this part plus this part, and because of the strict inequality, we do not exclude, we exclude 0 and 2, so 0 and 2 are not included. Now when it comes to the other one, now we want to solve this one. Indeed, this is always bigger than or equal to 0 because of the absolute value, but we don't need the equal case here, so we have to exclude the equal case because it requires not equal to 0. So the only value of x making this equal to 0 is x equal to 2. So then we don't want this to be 0, so it means x should not be equal to 2. So the solution will be all real numbers except x equal to 2. So then the solution of this will be all real numbers, so x belongs to the set all real numbers except 2. Because if you put 2 here, there will be equality, so 0 equal to 0. So, but we don't want this. So the domain should be now the all real numbers except 2. So all real numbers except 2 can be written in this way. Now let's look at this try and check. We can follow the same path. We have a logarithm and we want to find the domain. So this which values of x makes this one bigger than 0. So we check this one, and when you solve this one, it requires some solving skills, and we had We learned them in Math 1. Now x is less than 5/2, and this gives us the interval from -infinity to 5/2, and 5/2 is not included. So the domain here should be -infinity to 5/2. Now we can look at your x minus x squared bigger than 0. So you find the roots here, and I will skip defining the root issue because this is standard in standard form. So you find the roots of this polynomial, and then you find 0 and 1, and you put some values. You will get this is minus, this is plus. I'm skipping also this step. Okay, you can check. And what we want here is this part, in 0 not included and 1 is not included. So this will be the domain. So here it will be 0, 1, and this is -infinity to 5/2. Now when it comes to your the ln x plus 1 should be bigger than 0. But for all numbers, for all x element of real numbers, and for all real numbers, this is true, the equality. But we don't want the equality here, so we want the strict bigger than. It should be strictly bigger than. So we have to exclude this case here. X plus 1 should not be equal to 0 here. So you can say, what does this mean? This is already true. This means like x can be anything, but x should not be equal to, it's satisfying this, so x should not be equal to -1. So you can say x can be anything but -1. So here, if you write it in interval notation, it will be -infinity to -1 union -1 to infinity. So the domain here will be -infinity to -1 union -1 to infinity. Now, properties of logarithmic functions. Okay, this is an important part. You have to know these properties. Now, you can deduce, or you can get these properties by applying the exponential form. Look at here, this b10. What does this mean? b20 is always 1, right? I mean, b20 is always 1, and you write it this way. Log base b of 1 is equal to 0, right? Because of this. And this is also true because b2x is equal to b2x, right? So which power of b makes b2x? Just the power x, right? So this is straightforward. And look at here, which power of b makes b? It's the first power, of course, right? Because b to 1 is equal to b. And here, b to the log b of x is equal to x. And this is an interesting power. I mean, look, here, the idea comes from here. What is this? This is standing for the power of b, like power such that b to that power is equal to x. So now you're taking this power to the b, so you know it's b to that power is already x, so you get back to x. Or if you want to use some exponential approach, your direct approach, you can say it this way. You write log b of x is equal to log b of x. Now take this as power, take this one as power here. So you write the exponential form. You say b, the base, to the power log base of x is equal to this x here. So you can get this here. This is just a trick, like you use this one, like log b of x is equal to log b of x, and then try to write this one. I mean, take this one as a power, I mean as a number, and try to write it in exponential form. You will get this one. And here we have some more things. This log b of m times n is equal to log b of m, and log b plus log b log base b of n. Now, this is the product rule, so it's coming from here. Okay. If b to a, okay, it will take some time to explain this one, but anyway. If you multiply these two, like you will get bx plus y is equal to m times n. So when you write here log base b of x plus y and log base b, so you will get this x plus y. This is the power. But what is x? X is indeed log base b of m, and this is log base b of n. This is y, this is x from here, from this assumption, so you get this one. I mean, when you replace x with log and then y with log, and then you get this one. And in the same way, we have this log base b of m over n equal to log base b m of m minus log base b of n. Now, you don't have to know the derivation of these things, but these are the rules you have to apply, and you have to memorize. Right? If you know where do they come from, it will be good for you. But if you don't understand, okay, no need to pay more attention to it. Just remember these, okay? And log base b of m to p, m to the p power is equal to p times log base b of m. This is another thing. Yeah, it has also an explanation here like this. You can say let p is equal to b to x, and then x is log base bmp. But this one here, okay, we need to divide both sides with p, maybe. I mean, we do some more manipulation, and you got this one here again. Anyway. Okay, I don't remember now, but if you try, I mean, if we try, we can get this the equality as well. Okay. Now the properties of logarithmic functions. Let's see. Now we will check with this common and logarithm common and natural logarithms. Here, if you don't see the base, it means 10, and the log base e is ln. You know, ln means this ln x is again log base e of x, and if you ask what is e is about 2.71. Here, log of x means log base 10 of x. Okay, then. If we apply the rules here, the log base 10, 1. Okay, which power of 10 makes 1? It's 0. And which power of 10 makes 10? It's 1, the first power. And then which power of 10 to x? Which power of 10 is equal to 10 to x? Of course, x. And 10 to the log x, log 10x is equal to directly x. Yes, we get the same things, like you can apply these to e, and you will get these, like the important ones are like ln e to x is x, and this e to ln x is equal to x. Okay, let's use the logarithmic properties to simplify these expressions. Here, 10 to log base 10 x squared plus 1. Remember this log base b of a, and if you raise this one, I mean if you raise b to that power here with log b, then you get a, because this is the power of b that makes a. So when you put it as a power to b, so definitely it will give you a. So by using this, we can say this is equal to 10 to log 10 x squared plus 1 will give you x squared plus 1. Now how about this e2 log base e of x plus 3, and this will give you again x plus 3. I'm using this rule. Now it's the same. Okay, what is this? This is log base 10 of 10 to x to the 4th. Which power of 10 makes 10 to the x to the 4th? It is x to the 4th for sure. And we have the same issue here, log base e of e to x minus 1. Which power of e makes e to x minus 1? Say x minus 1. And which power of log, okay, 2, well, which power of 2 makes 2 cubed? You can write here 2 cubed, and you say it's 3 for sure, right? Okay, then now we will try to write each logarithmic expression as a sum or difference of simpler logarithms. Now we have to, okay, I want to remind you the rules. The first rule I would remind is this one here, log base b of m times n is equal to log base b of m plus log base b of n. So here you can use it here because there's a multiplication, so you can write this one as, okay, I will use it here. Now this is multiplication. I can separate them by addition. Now I can separate them. The next thing I can use here is, okay, how about dealing with this 4? And I can write this one as y to 1/2. So do I know anything about this log base of 2a? No, okay, let me write the rule. The rule is this: log base b of m to the p is equal to p times log base b of m. So it means I can take this power to the front. Now 4, I can, and 4 this 1/2. Now first I deal with this. I put the radical, I convert the radical to exponential form. That's 1/2. Then I use this formula here, so I can take them and I put them into the front. Now I cannot go further than this because this is the simplest term. This is the simplest in its simplest form. So this is the simplest form I can get from this expression. Now when it comes to the last one, we use the quotient rule. What does quotient rule says? Like if you have a logarithmic function here, then you can, if you have a fraction here, you can write this one as fraction. I mean this one as the numerator is here and numerator, and the denominator here, but we put here minus. Then you can take this 3 front, 4 front, and this is the simplest. Now let's do the same thing for these two expressions. Now we have a multiplication here, and then we have a logarithmic function, and then we can write here the logarithm b u cubed plus log b cube root of v, and then here I can write this one as a power of v. So you know this cube root means like the 1/3 power. And then I can take the powers to the front in the logarithm. So you've got this one here and 1/3 log base b of v. So this is the simplest form we can get. And we will do the same thing for the others. Now, for example, this one, since there's this is a logarithmic function, and we have a fraction, so you can write it this way, and 2 is 5 log y. Yeah, you can check the powers here. You can do this job if it's a pure power. Okay, don't try to make this one, for example. Don't take this one. No, you cannot, because it's addition here. So it's just one thing. So you cannot take, like, if it is like that, x cubed plus 5, you know, you're taking the power of everything here. So you can take this 5, not x cubed out. No. Now we will do this. We will do the reverse now. I mean, these are given to us. We want to make them a single logarithm. So we want to combine them to a single logarithm. Now we will do the reverse. You know, you can start with these. Like these are coming from the powers here, so we can put them back. And then we have addition. It will come to us as multiplication inside. Now look at here. Now 3 goes back to cube, 5 goes back to x as a power, and now this is addition, and the bases are same. Okay, this is important. The bases are same here. If the bases are same and you have plus here, you can put them together. Okay, it's first do the 8 and the x to the 5th. Anyway, so then you can combine them as multiplication. But here you can do it. Okay, you can do this thing. You can multiply these two if the bases are same. So you can put them here. So you cannot do this. No, they're the same. Don't do such thing. Now the next is here we deal with this. You know, you can leave the minus here, and this you can take this 1 or 2 as a power here. That will be x squared and y to 1/2, and then this is minus. This makes x ln x squared divided by y to 1/2. So then you can write the 1/2 as square root y. And let's do the last one. The last one is, okay, you can bring the powers, the coefficients as powers inside. So it will be the 2 will go inside, so it will be squared, and the 3 will go inside, and it will be z cubed. And now the bases are same, so we can combine these two as multiplication, and you can divide it by z cubed. So you combine these two, 5, you make this one, multiply the terms inside the logarithm, and then then this is, so it implies division here. This is this is subtraction, so we can write it as division here inside. So this one divided by this, so this is one single logarithm. There's one thing that's important. This is a common mistake the students do. They split this log m and log b base log base b, and they when it is added, they think it's added like the inside, no. And some students think that when you divide or you separate them this way, no, this is not true. We do it like this, you remember? Okay, let's do the try and check. You can write this one as what? ln x to the 7th minus ln 3y plus ln 3 goes to here, you can say 3 cubed, and these two will make ln, or you can anyway, let's do it this way. 3y plus ln 3 cubed, which is 27, then you can end up with this ln 27 x to the 7 divided by 3y. So you can do the fraction, then multiplication with this. So you will end up with ln 27 x to the 7th divided by 3y. This is the answer. Okay, thanks for watching.